All right, and I'm back. So we're going to talk about Dalton's law now. And so you'll need your gas law books for this. And this is another entry. I think the last one maybe that we wrote down or that you should have written down from the video last week was Graham's law of diffusion. If you didn't, you need to go back and watch the little video from last week because that's a law that you'll be responsible for knowing. The next one that we're going to write down, and this should be getting towards the end. I don't think there's any more. I'll go back and double check. But Dalton's law of partial pressures is the last gas law I think we're going to learn. Okay. So the plan is after we learn this one, I should be back Tuesday. We will start to go over the stuff. We'll go over any remaining questions that you have. My hope is that we'll do a little lab on Wednesday, maybe, and then review Thursday, have a test on Friday over gas laws. That's the plan. So Dalton's law of partial pressure, though, is the last one that we're going to go over. So let's get to it. Here we go. Let me pull this back up. Okay. And if you'll just follow along, write this in your book. And I'm going to be going over a couple of your problems from the assignment for today, the Dalton's law problems. So, okay, here we go. All right, so you'll need your booklets right here. And the entry for today is Dalton's law of partial pressures. Dalton's law of partial pressures. This law basically states that the sum total of pressures in a system come from all of the gases in that system. It's just accumulation of all the pressures exerted by all the gases in the system, okay? So it looks like this. If you're wanting to find the total pressure of a system, all you gotta do is add together all the pressures of all the gases in the system. So PT is equal to P1 plus P2 plus P3, dot, 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 however many gases are in there. So for instance, if you were going to go scuba diving and you get one of those scuba tanks that has like nitrogen gas in it and oxygen and a mixture of just a variety of gases, you could figure out the total pressure of the tank if you knew the pressures of all the gases in the system, okay? Now this looks like a super easy law, right? Yeah. Obviously, I'm not going to make it that easy, right? Because what if they don't just come out and tell you the pressures of each gas in the system? Which that's the thing. Rarely are they going to tell you exactly this gas gives off this much pressure and on and on and on. They'll give you lots of information about the gases there. Like they could tell you how much is there, how much it weighs, the temperature that it's at. But they may not tell you the pressure. So you got to figure that out and then plug it in. Ultimately, you plug it into this formula and solve to find total pressure. Okay, now before we try these out, just like the ideal gas law had like another little sidebar, this one also has something called a mole fraction, and it looks like this, okay? So this is the Dalton's law, but it's related to something called the mole fraction. The mole fraction, which looks like this, okay? Basically, chi, which is a Greek letter, this chi right here is just going to represent a number, like a proportional number, okay? Chi is equal to any gas in the system. So, for example, P1 divided by PT, okay? That's called the chi of that particular pressure. So let's say that P1 was like hydrogen gas. And in this particular system, you had hydrogen gas and ammonia gas, okay? And if I just wanted to know the pressure of just the hydrogen gas alone, you know, what's the pressure given off, what's the chi of that? It would be P1 divided by PT. And that almost gives you like a percentage, right? It's like if you got 10 out of 20 right, like on a quiz or something, you take 10 divided by 20, and that would give you 0.5. Okay? You would know that particular amount that you got right, those 10 points, that's about 0.5 of what there was available. okay? You can take the chi then, since it's just a ratio, like a measure, you can take it and apply it in another situation. The chi of a particular gas, so like the chi of P1 would also be related to its mole value. It would tell you how many moles there are. Okay, so the chi of P1, so this is the chi of P1, is equivalent to the chi of mole 1. Like they would be the same number and they're interchangeable. If you figured out your chi, your X of pressure of gas 1 to the total pressure of the system, that chi is the same proportion to the mole value. Okay, so like they're interchangeable. So we're going to try these out. We're going to look at some of these. Okay, and we'll talk about this. I'm hoping to show you a demo when I get back on Tuesday, and we'll put this law to work. Okay. All right, if I can remember. So I'm going to look at this sheet now. This is the one that I'm leaving with the sub for Monday, and I'll post it on the classroom as well. But it's Dalton's law of partial pressures. Okay, and we're going to look at a couple of problems today. We're going to look at problem number 1 and 2. And then I'm going to start you on number 4, but I'm not going to finish that one because you guys will totally figure it out. And you probably don't even need me. You probably can figure it out on your own, but we'll look at it. Okay, so we'll start with number 1. It says you've got a 250 ml sample of oxygen. So I'm going to go ahead and write that down. I've got a 250 ml sample of oxygen, O2. This sounds like a volume to me. Okay, it's collected over water at 25 degrees Celsius. So it tells me a temperature, 25 degrees Celsius, at 760 torr of pressure. Okay, what's the pressure of the dry gas alone? So they're asking for the pressure of the dry gas. So the pressure of the dry gas, I'm going to put PO2. When they talk about pressure of the dry gas, if they're saying they're having to collect it over water, not that they mean like you can have a wet gas versus a dry gas. I don't know, that strikes me as funny. Anyways, like wet farts. I should probably edit that out. Anyways, but you can have, you're talking about the oxygen, the O2, not necessarily the water vapor. Okay, does that make sense? Like if they're talking about the dry gas, they're not talking about the gas that's also there because of the water vapor. If you're collecting gas over water, if you're collecting a gas sample over water, you've got to think about the water that's in there too, because it's giving off particles, it's giving off vapors, which are going to have pressure. So they're not talking about the pressure caused by the water vapor. They're talking about the pressure caused by the other gas that they're collecting, which is the oxygen. So they want to know, well, what's the oxygen's pressure? Okay, so they give you this other little piece of advice. They say, hey, the vapor pressure of water, by the way, at 25 degrees Celsius is 23.8 torr. So they're also telling you that you've got pressure of water here. That is 23.8 torr. Okay. All right. So here's the thing. They mention like 3 different pressures in this problem. They talk about collecting gas over water, and that has a total pressure of 760 torr. They talk about one of the gases is the dry gas, the oxygen. One of the gases is the water vapor pressure gas, right? So the gas that's being collected is one that you got, and that's the one they're wanting to know about. And then you got the water vapor pressure gas. Well, what's the total pressure of the system? They said here it was 760 torr. So for this particular problem, really, you've got a lot of numbers here, but you only need like 2 of them. You need the total pressure of the system. This was the total pressure of the system. And then you're going to be needing these 2. All right. We know that the total pressure of a system is equal to the gases that are involved. And in this particular case, it's going to be the water vapor gas and the oxygen gas, right? So I could plug in 760 and set it equal to, I know that the pressure that's exerted by water is 23.8 torr, plus I don't know the pressure of the oxygen gas, right? So in this particular case, you really do just solve to find the pressure of the oxygen, right? You're just going to plug in some real simple algebra there and solve to find the pressure of the oxygen gas, okay? So that's number one. Number one really is that simple. Now, the rest of them are not going to be that way, but they're not that much harder. So let's take a look at number two, okay? So problem number two on your worksheet says you've got a 32 milliliter sample of hydrogen that's collected over water at 20 degrees Celsius and 750 torr of pressure. What's the volume of the dry gas at STP? What? Okay, so let's just start writing stuff down. They give you a sample of hydrogen gas, and it's a 32 mil sample. So I'm going to go ahead and say, okay, that's my volume. It's 32 milliliters, and that's hydrogen gas, right? Okay, it's collected over water at 20 degrees Celsius. That's my temperature, 20 degrees Celsius, and 750 torr of pressure. And here's the thing. All of these conditions, really, you're looking at the hydrogen gas, okay? And they want to know what's the volume of this dry gas. They want to know what's the volume of the dry gas at standard temperature and pressure. So now what they're doing is they're changing the temperature and the pressure to different conditions. So the new temperature, if it's standard temperature, what is it, guys? What is standard temperature? It's just 0 degrees Celsius or 273 Kelvin, right? What's standard pressure? Well, it's 1 atmosphere. Or since you've already got the unit in torr over here, we're going to switch this over to torr and just say this is 760 torr. Okay. I'm going to go back over here, and while I'm fixing stuff, I'm going to go ahead and fix my temperature. I'm going to add 273. So this is going to be 293 Kelvin. So I've got two sides to this equation. All right. I got two pressures, two temperatures, two volumes. Now here's the problem though. That 750 torr, they say that is the gas collection of the hydrogen gas over water. Well, if you were paying attention to the problem we just did, we said if you're collecting a gas over a water sample, that dry gas is not the only one there, right? You've got gas produced from the water, like water vapor, right? So we really just want the pressure caused from, we really just want the pressure of the hydrogen gas, right? So what I'm going to do here is I'm going to go over here and I am going to change this pressure, this one right here, the 750 torr, and I want to take out of it the water vapor pressure. I want to take away the water vapor pressure, okay? So if I take that out, and they say the water vapor pressure there on that problem is 17.5. I'm going to get rid of it over here, 17.5. And when you do that, that's going to leave you with, I need you guys to do quick math faster than me. I'm going to screw this up and you guys are going to make fun of me. I'm going to use my calculator because I don't want to hear it from Nikki. Not that she would. It'd probably be Jimmy. Maybe Clara. I don't know. Minus 17.5. Okay, so 732.5 torr. Okay, that's the pressure of the dry gas when it was collected over water. We got rid of the water vapor out of it. Now, why don't we have to do that to the other side? Because they're telling you it's a dry gas. They're not collecting this other side of information over water. So you don't have to worry about water vapor pressure on the other side of that problem. Okay? You only have to get rid of it if they mention, hey, this is the gas collected over water. So the pressure caused from just the hydrogen gas is 732.5 torr. Okay? So now that we've got that, though, we still haven't solved our problem. Like, we've got to find volume. What's the new volume of this hydrogen gas if you decrease the temperature, but you've increased the pressure? Okay. So look at what you've got. You've got 2 sets of pressure, 2 sets of temperature, and 2 sets of volume. If we only had a gas law that had 2 pressures, 2 volumes, and 2 temperatures. Eureka! We do. Okay. And it's called the combined gas law. So you end up ultimately having to use the combined gas law to figure out this problem. Okay, and remember the combined gas law is this one. Okay, P1B1 is equal, or over T1 is equal to P2B2 over T2. Okay, and then you just start chunking numbers in there. Because of the fact that this is not the ideal gas law, as long as the units are the same on both sides, you really don't have to worry about what they are. Like, you could have temperature, well, temperature has to be in Kelvin, but you could have pressure in like torrs or ATMs, pascals. You could have the volume in milliliters or liters or cubic centimeters. So let's just start plugging stuff in, as long as we have the same units on both sides. Here we go. So I'm going to write this, I think, over here. Just remember, I'm looking for volume. So I'm going to plug in my pressures here. I've got 732.5 times my volume of the first set of conditions, which is 32 milliliters, divided by my temperature, which is 293, and set it equal to my new pressure, which we said is 760 torr, times the new volume, which we don't know, right? We're looking for, over my new temperature, which we said is 273. Okay. Now, having said all that, at this point is where most kids will make their mistakes. They're like, oh, I know how to do this. I hope that you do. And so you better take your time and do it right. But you'll just go ahead and solve to find your missing variable, your V2. Okay. So what I'm going to do, I'm going to do all the stuff on the left side of the equation. So 732.5 times 32, and then divided by 293. And I end up getting 80 for this side. Okay. So on this side, I'm going to erase this. I end up getting 80 is equal to, I'm going to do 760 V2 over 273. And then I'm just going to bring this right there and multiply 80 times 273. End up getting 21,840. 21,840 is equal to 760 V2. And then, of course, you just solve to find V2. Okay. So my new volume of this gas under new conditions is around 28.74. How many did we start with? Did we start with 3 digits? Anyways, but what's the unit going to be? Well, you go back and you look, what was our unit in the original? It was milliliters, right? Okay. So, and then you need to ask yourself, all right, what would we expect if the pressure from one side, from the beginning to the end, pressure went up, right? So if we know anything about the relationship between pressure and volume, if pressure goes up, volume should go down if there's not too much of a change in temperature, and that's exactly what happened. The volume went down by just a smidge. So under these new conditions, the volume of the hydrogen gas, the dry gas, would be around 28.7 milliliters. Okay. All right. That's how you're going to work like problems 3, or problem 3, and then we'll have some more review problems like that later this week. When you get to number 4, that's a mole fraction problem. And if you look at all the stuff that you've got, it says that you've got a mixture of 2 moles of hydrogen, 3 moles of NH3, 4 moles of CO2, 5 moles of N2, and exerts a total pressure of 800 torr. What's the partial pressure of each gas? This is where your mole fraction is going to come into play. Okay, so for problem number 4, if you've got 2 moles of H2, 3 moles of NH3, 4 moles of CO2, and 5 moles of N2. And they say all of this together gives off a total pressure of PT of 800 torr, right? They want to know what's the partial pressure of each gas. So they're looking for partial pressures of each one of these. So they want to know the pressure of hydrogen, the pressure of NH3, and so on and so forth, okay? So if you know anything about the mole fraction, you know, well, if you know the moles amounts, it could be used to figure out your pressures because they're related by using a mole fraction, a chi, all right? So we know that the chi, if you have the chi of, like, for instance, hydrogen gas, the moles, if you know the moles of hydrogen gas divided by the total moles of the system, this could be used to figure out pressures, right? They're related. Okay. So do we know the moles of hydrogen? Sure. We know that it's 2. We got 2 moles of hydrogen. And we know that the total moles of the system is just what? 2 plus 3 is 5, plus 9 is 14. So 2 divided by 14. So 2 divided by 14. It's going to be about 0.143. So that's the chi specifically for hydrogen gas. For this system, the mole fraction for hydrogen gas is 0.143. And remember, that's just like a proportion. It's telling you this is the proportion of hydrogen gas that's present. Well, you can use that chi, that mole fraction, plug it in to the pressure chi, and you can solve to find your partial pressure of hydrogen. So we'll take this number right here, 0.143, and it has no units. We're going to plug it in right here. So 0.143. And then we know that the total pressure of the whole system from all these gases is 800 torr, right? And so now at this point, can you solve to find pressure caused from the hydrogen? All right. So I'm just going to do 0.143 times about 800. And that tells me the pressure caused from the hydrogen gas, is about 114.4, but 114 torr of pressure. That's my pressure of the hydrogen gas. So here's the thing. They want you to do this for every gas that's there. So that's what you need to do. Okay. Good luck. I hope to see you on Tuesday. Okay. Hopefully.